Good evening, everyone. This is Krishnan, and I am pleased to be your moderator today. We are fortunate to have with us Devang Bajpai, who will be sharing insights on topic traceless, traceless symmetric tensors and approach to legendary polynomials and uh, spherical harmonics. So, please join me with welcoming Devang Bajpai. Devang Bajpai, please continue.
Thank you, Krishna, for introducing me. So I will start from stating some results from my previous talk. Now I have shown that by using traceless symmetric tensor, we can expand any function of angle in the following manner. Now in this expansion, the coefficients are called the tensors, and the indices are sum from 1 to 3 as Cartesian indices, and the unit vector n hat is given by this equation. Now, in standard approach, any arbitrary function of theta and phi is expanded in spherical harmonics in the following manner. Now, I've also shown that the eigenvalue of our angular Laplacian will be given by minus L times L plus 1. And in standard approach, the spherical harmonic acting on an angular Laplacian also yields the same value. And L apparently has the same meaning in both formalism. Now, that means that there must exist some particular traceless symmetric tensor which must be equivalent to y, ln, theta, and phi. Now, our goal is to construct that tensor explicitly. Now, I have already shown that the number of linearly independent traceless symmetric tensor of rank L is given by 2L plus 1, which is not surprisingly equal to the number of y, ln function for a given L. That quantity m here is integer from minus L to L. So there are two L plus 1 possible values. We consider the first case of azimuthal symmetry, where our function of angle is invariant under the rotation about the axis, and hence independent of phi. In that case, within the standard treatment, the most general function can be expanded in Legendre polynomial. And here P you can see is called the Legendre polynomial. Now, Legendre polynomial are identical to spherical harmonics for n is equal to 0, except that they are normalized differently. Now, Legendre polynomial can also be written explicitly using Rodriguez formula given by this equation. In the traceless symmetric tensor formalism, the azimuthal symmetry case must be described by the traceless symmetric tensor that are invariant under the rotation about the z-axis. Now, it is easy to begin by thinking about L is equal to 1, where we are seeking a tensor of rank 1 with one index, and such a tensor will be a vector, which is in the sense a tensor of rank 1. It is obvious that the only vector that is invariant under the rotation about the z-axis is the vector that points along the z-axis. Now, I will denote such a unit vector with the z hat, and this vector will point along the z direction. Now, previously you have noticed that I have denoted such a unit vector with ex hat and ey hat, ez hat, but now I am denoting it with z hat. So here you can find that there is inconsistency in my notation. But this inconsistency was intentional with two motivations. First, previously we never needed a notation for the components of a unit basis vector, but here we will. So it will be a real thing to write a components like ez hat I. And second, later I will describe a convenient way to construct a basis for the traceless symmetric tensor, which involves the use for a basis for a vector consistency of z hat and two complex vectors. So the use of z hat rather than the e z hat will remind us that we are thinking about the u positive u minus n z hat basis rather than ex hat, ey hat, and ez hat basis. Now, here z hat I is the ith component of the z hat, resulting function of n hat then will be given by this equation. Now, to generalize this to any arbitrary L, we can construct a tensor of rank L that is invariant under the rotation about the z-axis by considering the product of simultaneous vectors This is clearly symmetric, but it is not traceless. However, one can make it traceless. So, however, one can make it traceless by subtracting some delta function by it. Now, here I will denote the traceless part of this tensor by the curly braces, and the traceless symmetric part is constructed by starting with the original expression and then subtracting the terms proportional to one or more canonical delta function, where the subtractions are uniquely determined to require by the expression to be the traceless. Now, it gets rather complicated to describe how this can be done for a it's rather get complicated to describe how this can be done for a general symmetric tensor of arbitrary rank. So I will just illustrate it by example. Now, the tensor of rank 0 and 1 is a scalar and vector by definition. So they are traceless in by itself. But for rank 2 tensor, the trace of z hat I and z hat j is equal to 1. But we can subtract a constant time delta function so that the result is traceless. Now, in third term, you can say that the coefficient is 1 by 3 because the trace of delta function is 3. Now, for rank 3 tensor, that is our fourth term, the trace will be z hat k, but we can make it traceless with the subtraction. Now, here I have subtracted the 1 by 5 times the sum terms that are symmetrized in the delta function. Now, to verify that 1 by 5 is the right coefficient to make the expression traceless, we can take its trace and we will find that we get the expression to be equal to 0. Now, for rank 4, there is an option of subtracting terms with either one or more two canonical delta function, and both are needed to give a traceless result. We can start with arbitrary coefficient and see that what they have to be. Now, within each set of parentheses, we will find that the term chosen to be make the expression symmetric in I, J, K, and M. If we calculate this over and over I and K, we will find two constants. One will be C1 and other will be C2. And if we compute for the expression to be vanished for K and M, we will find that the expression must be separately give us the C1 equal to minus 1 by 7 and C2 is equal to 1 by 35. Now further we can also calculate the terms and we will find that in the last term here the constant is equal to 1 by 7 and 1 by 35. Now we will argue later that the equation gives only the traceless symmetric tensor that are invariant under the rotation about the axis. And therefore, we can write a function of a unit vector in terms of these tensors. Now, the function here is the only function up to the multiplicative constant that is symmetric and satisfy the condition of our eigenvalue. Since the PL cos theta is asymmetry, symmetric, and satisfied, then we can easily switch between here the FL and the PL. Then we can find that we can write the above equation in terms of our Legendre polynomial easily, where the constant is yet to be determined. Now, both sides of equation 4 are polynomial in cos theta, where the highest power is cos L theta. If we can find the coefficient of this highest power on each side of the equation, we can determine the constant. On the right hand side, the highest power comes entirely from the traceless part of the term in the now in the right hand side, the highest power comes entirely from the traceless part in terms of the traceless symmetric tensor. Now, since all the other terms contain canonical delta function, which result in the factor of a form of n hat dot n is equal to 1. Now, reducing the number of n hat vector available to give the power of cos theta. So, the leading term on the right hand side is simply constant times z hat dot n hat dot to the power is equal to constant times cos L theta. Now, for left hand side, we can use Rodriguez formula to extract the highest power. And if we compute the derivative, we will find the result will be equal to 2l factorial upon 2 to the power l factorial square xl plus some lower powers. Now, matching this coefficient, we will find that a Legendre polynomial can be written in the unit vector tensors. Now we can return to the journal case, in which there is no asymmetric symmetry and the expansion requires the spherical harmonics YLM. Now YLM are chosen to have a very simple dependence on phi, namely in which the spherical harmonics are proportional to the e to the power I infinity. Now this property can be described in terms of how the function transforms under the rotation of a coordinate system about the z-axis. Under a rotation by an angle psi about the z-axis, the angle phi changes by a sign, and y changes by the factor of e to the power I. Now, I have not been careful here about specifying the sign of this rotation because it will be easy to fit sign convention at the end. The important point here is that if we want to match the convention of the spherical harmonics, we need to construct a traceless symmetric tensor that are modified by the rotation only by the multiplicative phase factor. That is, we are looking for a tensor that are complex and that are eigenvector of the rotation operator. Naturally, we will begin by considering a vector which are under a rotation about the z-axis transformed in a following manner. We thus seek an eigenvector of the following matrix, which is our rotation matrix. Now, eigenvalues lambda of the matrix are determined by the characteristic equation given by this equation. Here, I is the identity matrix, and if we expand our characteristic equation, we will find the following equation, for which the solution will be e to the power plus minus I psi. Now, eigenvector is formed by the characteristic equation gives the following equation. Now, if I simplify this equation, I will find that my equation take the form of this equation. Now, for this, we can see that easily that our y component of the vector is equal to plus minus I times Vx, which is x component of our vector. Now, constructing the normalized eigenvector, we can define new quantity that will be u hat positive and u hat negative, which will be given by this equation. Now, they are orthonormal unit vector, and by orthonormality, I mean that complex conjugation of this vector multiplied with this vector yields a delta function. Now, we can complete a basis for a three-dimensional vector by adding the z component also. Now, one can ask that how we should visualize a vector with the imaginary components and what direction does it point? It certainly points in the definite direction in the complex three-dimensional space, which is equivalent to six-dimensional real valued space. But for our purposes, we don't need a geometric picture of these kinds of vectors. We are simply going to use them to form the dot product and to construct a complex valued function of theta and phi. Now, note that the complex conjugation as used in the previous equation is essential for defining a positive definite norm of a complex vector. And the quantities u hat positive and u hat positive when dot with the same quantities yields a 0. This leads us to the convenient fact that the tensor we choose is both symmetric and traceless. Now, if we dot this unit vector with the n hat, we will find the following result. We can construct a function proportional to the e to the power I and phi for m greater than 0 by including m factors of u positive and arranging for each of them to be dotted in n hat. This can be done by considering the function defined by this equation. Now, see that in this expression, every complex vector is dotted with the n hat. We can find that the complex vector when dotted with the z hat gives us a 0. Now, so when the right hand side is expanded and all the indices are summed to give the dot product, the only term that survives are those for which every u positive is dotted to the z hat. Thus, the right hand side of this equation is proportional to the e to the power I infinity. Now we know that the right hand side of the above equation is the eigenfunction of angular Laplace with eigenvalue minus L times L plus 1. Now I will argue below that Any such eigenvector that is proportional to the e to the power I and phi is necessarily proportional to y. We will return to the question of uniqueness, but first let us assume that the uniqueness holds, so that our function of angle is proportional to the spherical harmonic. As in the previous derivation for Legendre polynomial, we can determine the constant of proportionality by matching the leading term in the expansion of both sides of the equation, and we can write our function of angle in terms of sine theta to the power n e to the power I and phi times the polynomial in cos theta. So we can use the highest power of cos theta to determine the matching. Now it is easy to extract the leading terms of this equation because it comes from the first term in the expansion. Now the first term gives the highest power of cos theta because the frontal delta function that appear in the later term cause one or more unit vector to dot with the other unit vector. Now reducing the number of unit vectors available to appear in the form of n hat dot v hat is equal to cos theta. Thus we will find that our function of angle takes the following. Now to compare this equation with the leading term in the expansion for the standard spherical harmonics, we need a formula for y element theta and phi, which will be this. Now here you can see that PL to the power n cos theta is the associated Legendre function, which can be defined by this equation. Now using the same technique we used previously, we can here compute the L plus m derivative of x squared minus 1 to the power n. And if we match the coefficient of this term, we find that we can write that for positive m, a spherical harmonics can be written in terms of our tensors, where our tensor is now dln times this. So it is part of the complex unit vector dotted with the z hat. Now, for negative values of m, the calculation will be identical, except that we will use u negative instead of u positive. And our result will take the following. Now, it is worth mentioning that the curly braces indicated the traceless symmetric part can be put on either factor or both in the expression. That is, now, where the top line is justified because the traceless symmetric part differs from the trace part only by the term proportional to counter delta function, which give no contribution when summed with the traceless symmetric tensor. Similarly, once the second factor is written in traceless symmetric form, there is no longer need to take the traceless symmetric part of the first term, since the traceless symmetric part differs from the only term proportional to the conical delta function, which vanishes when summed with the traceless symmetric tensors. Finally, we can return to the question of uniqueness. In asserting that a function of angle is proportional to the spherical harmonic, we know that both the functions are proportional to the e to the power I and phi. And both the eigenfunctions of the operator, that is our angular Laplacian, with eigenvalue minus L times L plus 1. Now we claim that up to the multiplicative constant, there is only a one function that has this property. Assuming that the power series representation of equation 1 always exists, the uniqueness that is easy to see. We have showed that the number of linearly independent traceless symmetric tensor of rank L is 2L plus 1, and now we have constructed 2L plus 1 such tensors. Now, here M takes the value from minus L to N. Thus, clearly linearly independent traceless tensor with eigenfunction of rotation about the z-axis with different eigenvalues. Thus, any traceless symmetric tensor of rank L must be a linear sum of the tensor in our basis. When we also specify the tensor being sought is an eigenvector of the rotation about the z-axis with specific eigenvalue, then only the one of the tensor in our basis can be contributed. Now, the previous argument is solid, But one might still wonder what happens if we try, for example, to construct a different tensor by using both u positive and u negative in the same expression. For example, we might consider u hat positive and u hat negative, which is invariant about the rotation about the axis. And with a little work, one can show that easily that this will be equal to minus 1 by 2 times the traceless symmetric part of the z hat I and z hat. Now to summarize this whole thing, we can now say that the function of theta alone without phi can be expanded in the following manner. And here the CLs are the constant. This corresponds to what is standardly called expansion in Legendre polynomial. Now, I have showed that exactly how to relate these terms to the standard convention for normalizing the Legendre polynomial. But we can see here exactly what these functions are. Now, using this relation, we have found that the whole equation is the Traceless symmetric form. Now, up to a normalization convention, these are the Legendre polynomials. Now, we will start with the multipole expansion. Now, in previous talk, we have shown that the most general solution to the Laplace equation is spherical coordinate was given by this equation. Now, I wish to apply that result to a common situation. Suppose we have a charged object and we wish to describe the potential outside the object. Let's say for definiteness that the charge of the object is entirely contained within the sphere of radius r, centered at the origin. In that case, Laplace equation will hold for all r greater than r. So there should be a solution of the form of this equation that is valid throughout this region. At the infinity, the potential of a localized charge distribution will always approach to a constant, which we can take to the zero. We can see that the here coefficient that appears in this equation must all vanish, and the BF factor can be observed in the redefinition of our tensor. So we can write the expansion in the following manner. Since each successive term comes with an extra factor of 1 by r, at large distance, the sum is dominated by the first few terms and maybe the first few terms. All the information about the charge distribution of the object is contained in our tensor. So the knowledge of first few tensors is enough to describe the field at a large distance, no matter how complicated the object is. Now the first few terms of this series have a special name. For L is equal to 0, the term is monopole term. For L is equal to 1, term is dipole. And for L is equal to 2, the term is quadrupole. And for L is equal to 3, the term is octupole. If we want to calculate the tensor in terms of charge distribution, we can start with the general equation for a potential for any arbitrary charge distribution. Now, the multipole expansion can be derived by expanding 1 by r in power series of r. Now, here this curly r denotes that we have subtracted the r vector with the r prime vector. And here I have followed the notation of Griffiths. So I will begin by doing as Griffith does, which is the simplest but not the most useful form for the multipole expansion. Now, what Griffith does, he rewrote the denominator in the following manner, where r and r prime are the length of the vector r and r prime, respectively, and theta is the angle between these vectors. Now here boldface denotes the vectors. Next, he used the fact that the Legendre polynomial can be defined by generating the function, which will be given by g of x and lambda, which is defined by this equation, which means that the Legendre polynomial can be obtained by expanding this g of x and lambda in a power series of lambda. Now, this equation is sometimes also taken as the definition of Legendre polynomial, and sometimes it is derived from another definition. In any case, if we accept our equation to be valid, then we can write 1 by r term in terms of our Legendre polynomials. Now, inserting this relation to our equation of potential, we will find our potential takes the form of this equation. Now, this is the easiest way that we can show that there is an expansion for potential in powers of 1 by r. But the complication here is that the cos theta prime appears inside the integral. If we could implement this equation, we could easily able to calculate a smallest number of quantities of our tensor, and then we would be able to evaluate our potential at a large distance in any direction. Now, to use this equation directly, however, one would have to repeat the integration, and if we repeat our integration for every direction of r, we can easily extract the monopole and dipole, which gives us just by massaging the formula to extract the monopole and dipole. But the standard method of improving this equation is to use the spherical harmonics. But here I will derive the equivalent relation using the traceless symmetric tensor approach. Instead of expanding 1 by r in powers of r prime, we will think of it as a function of a three variable, the components ri prime and the r prime. And we will expand it as a Taylor series in a three variable. To make the formalism clear, I will define the function f of r, which will be equivalent to 1 by r. Now, the function then can be expanded in the power series using the standard multivariable Taylor expansion, where the repeated indices are summed. To separate the angular behavior, we have written our x prime I to be equivalent to r prime times the NU. Now, our above equation becomes the following form. Now, the notation can now be simplified by noting that the f is a function of r vector minus r prime vector. The derivative with respect to xi prime can be replaced by the derivative with respect to xi only. With a change of sign, we will find that our series take the following form. Now, this allows us to write all the derivatives in the expansions much more simply. Now, the L term is to be formed by repeating the above operation L times. Now, combining equation 13 with 12, we can easily write our 1 by r term in the following manner. And now you can see that the quantity here in parentheses is the traceless, because if we will compute angular Laplacian on it, we will find that this gives a 0. And we have already know that the Laplacian acting on a 1 by r vector gives us the 0, except at r is equal to 0. So we can see that the traceless symmetric tensor formalism to be emerging. Now, to evaluate this quantity, we will work out first several terms until we recognize our r vector, and we will adopt the abbreviation. Now, it is useful to start by evaluating the derivative of the basic quantities like r and n at I. And we will find such kinds of relation. It is then straightforward to show that these results exist. Now, here the thing in the bracket denotes the traceless symmetric part, and relevant cases are shown explicitly. Now, it becomes clear that the general formula, which can be proven by induction, will be given by this equation, where this double factorial can be evaluated in such a manner. Now, one can write this more symmetrically by writing this 1 over term in the following manner. Now, since the traceless symmetric part differs from the without trace part, that is proportional to the canonical delta function, which vanishes when summed with the traceless tensor. Now, starting with this equation, one can, if wish, drop the curly bracket around either factor and write it more symmetrically. Now, inserting this expression for 1 by r into our older equation for potential, we have the final result of our potential, where our tensor can be represented by the following equation. Now note that the coefficient in the above expression can also be written in the following manner. Now, for the purpose of illustration, I will write out the first few terms, that will be the monopole and dipole term, in a more detail. Now, the monopole term will be defined by this equation, where our charge will be the scalar and rank 0 tensor. Now, for dipole term, we have these results, and our dipole is a rank 1 tensor with a vector, which can be stated by this equation. So I think the meeting is going to end. So you all can rejoin this.
Yes, can you hear me now?
Yes, now you can ask your question.
Yes, so I was just saying, so basically what you do is you expand the spherical harmonics in terms of your traceless symmetric tensors uh, of some rank, and you see that the number of these will not exceed, let's say, 12 plus 1. Yes, am I right?
Yes, yes.
And this is very similar to what you have in quantum mechanics with angular momentum operator. Let's say LZ, you have taken azimuthal symmetry. So let's say LZ. LZ is just LZ on acting on size, just h bar L plus 1 times psi, and psi is written as some phase factor times Legendre polynomials, and you expand in that manner as well. So I'm assuming you can do your symmetric test list example in that case as well. Anyways, this thing, and
Yeah, yeah.
yeah, yeah. Anyways, I'm fine with it. I don't have any questions. No, I guess
So
so can you can end this.
shall
Thank
I?
you, Devang. Yeah,
Okay.
okay. Thank you.
So thank you for your